So welcome everyone. In this session, we have Mary Hu, data scientist at Microsoft, presenting towards inclusive software engineering through A/B testing, a case study. Just a quick note that please post your questions to the Q&A box instead of the chat. Mary, a reminder to start your timer and then off to you.
Sounds good. Hello everyone, welcome to this session. My name is Mary Hu. I'm a data scientist at Microsoft. With my co-presenter Irina, who unfortunately can't be here today, we would like to present our study towards inclusive software engineering through A/B testing. First, we would like to thank all of our collaborators, Christina, Chui, Shivam, and Paul. Engineering software features to be inclusive of all those that might, could, or should use it is very important. However, today, data used to engineer these features can have inherent biases with inclusiveness concerns, for example, gender identity. Using real-world data from the Windows out-of-box experience, Huibin for short, we present a case study of how inclusiveness concerns can manifest in A/B testing. We show practical adjustments to A/B testing towards inclusive software engineering and some insights into ongoing challenges. We all know or can all easily imagine that biases can exist, but how prevalent are they? We will get into a few examples next. First, from a 2017 research paper by Rachel Techman, we can see that Google's speech recognition app has been found to be more accurate for males than females. 70% more accurate, actually. Very, very, very different. Another example is face recognition. From a paper published in 2018, we can see that 3 commercial face recognition systems from IBM, Microsoft, and Face++ have all been found to classify males more accurately than females. How much more accurate? The maximum error rate for lighter-skinned males is 0.8%, while for darker-skinned females, it is 34.7%, significantly different. Knowing all this, our Windows experimentation platform is striving to identify and expose fairness and equality issues and to adjust the engineering process and policies to compensate. A/B testing is a data-centric software engineering technique, which is being used by many organizations to design and improve their software. It is the gold standard for evaluating the causal impact of changes, empowering organizations to make data-driven decisions about their software. In its simplest form, an A/B test randomly assigns users one of the 2 variants of a feature. Control group gets variant A, which is usually the default experience, and the treatment group gets variant B. User interaction with the 2 software variants are then recorded from that. Metrics are computed and compared. If the A/B test was designed and executed correctly, the only difference between the 2 variants is the change in the specific feature. Our case study is about the Windows out-of-box experience. Huibin helps users that are new to their Windows devices to set up their Windows accounts and services. Historically, Huibin has utilized a blue design in darker colors. And we all heard that darker themes are trendy. You can see in this slide how interest has been exponentially rising for darker modes over time in different searches. However, the themes can be reflective of gender biases, as you can see in this slide. The metrics collected for different product users when asked to state their preferences show clearly that women prefer lighter themes and men prefer darker themes. Back to our case study, in 2018, the Huibin feature team considered an alternative light design featuring additional graphics and a lighter color scheme. So here you can see what the old Huibin was looking like. This is the old darker and blue experience that you would get through when you set up your new Windows PC. And in this slide, you can see the new version tested, the white light scheme. So the goal of this Huibin design change was to increase the Windows service linking and signups, as measured by the proportion of users who link and sign up for those services. During the development process, the engineering team used an initial small-scale A/B test to evaluate the 2 designs using usertesting.com, which is an online user testing platform. The test was statistically powered to detect roughly a 15% change in the sign-up rates, with each variant having about 150 participants. They were recruited with the criteria of having recently purchased a Windows PC. The initial analysis of the results, a summary of which is shown on this slide, indicated no statistically significant differences between the two designs. However, a closer examination of the data along demographic slices indicated large differences along gender identity. The two biggest differences were with the OneDrive screen and the Office 365 screen. For OneDrive, those self-identified as female had 18% higher opt-in rate for the light scheme, versus those who self-identified as male had 21% lower opt-in rate. Similarly, for Office 365, those self-identified as female had 39% higher opt-in rate for light scheme, with those self-identified as male had 39% lower opt-in. This A/B test unintentionally recruited a balanced 50-50 split in gender identity, which enabled these insights. However, in general, A/B tests are conducted with random sampling, which may or may not be balanced on gender. For example, given the inherent underrepresentation of females in computing datasets, the overall results would likely have been the blue design becoming better. There are many other products with dark light theme that you can imagine potentially biases can exist elsewhere as well. For example, Teams, Outlook, Edge, the browser. So now the question becomes, how do we ensure software engineers get these important insights? And how do we help engineers to engineer softwares to be more fair and more equitable? So now let's take a look at our platform. At Microsoft, we leverage randomized control trials to ensure the new features we ship improve users' experience. You may be more familiar with the randomized control trials we run in products like Bing, MSN, and other online services. But we are also doing it in Windows, the operating system, with the users who are in our insider population. We have a well-established pipeline to help guide engineers through creating new features, running randomized control trials to understand its real impact on users, and to deploy the winning variant. We call this end-to-end pipeline the Windows experimentation platform. So how does the learning we got from this case study play a role in the Windows experimentation platform? First, it impacts how we plan for an experiment. If you're familiar with how experimentation works, one of the preparation steps before launching an experiment is to determine how big a population we need to target. We do that through power calculation. Basically, what a power calculation does is telling you to detect X% delta in a particular metric, you need to go to Y number of devices. Prior to this study, we used to only do the power calculation at the overall level. But now, as we have learned from the case study that different segments can perform differently, we will do separate power calculations on key subgroups as well. For example, to detect 1% improvement in battery life, we may need 100,000 devices if we do the power calculation at the overall level. But when we look at subgroups, it may take 70,000 devices in the US and 80,000 in the rest of the world, and making the total number of devices needed to be 150,000. The second impact on the platform from this case study is that it impacts how we conduct our analysis. When looking at the scorecard, we feed in some key segments that we care about, both from the business perspective and the data science perspective. If there is any significant movement in a subgroup compared to others, we will get alerted on the scorecard so that the data scientists on the experimentation team can partner with the feature team to do a deep dive analysis and better understand if the feature is truly impacting a subgroup of the users more than the others. In addition to the alerting itself, we can also slice the scorecard by the segments we care about to take a holistic look at the impact the feature has on the subgroups of the users. For example, this is the scorecard for the case study that I just walked through earlier. The first section of the scorecard is for overall users. The second is for female, and the third is for male. If the metric is highlighted with yellow, it means the metric has a statistically significant movement, meaning it has a p-value less than 0.05. We can see that at the overall level, there was barely any stat-sig movement for any metrics, but all the average metrics had stat-sig movement when we look at the genders separately. More interestingly, if we look at the female scorecard, we see that all the metrics have higher value in the treatment compared to control, whereas in the male section, all the metrics have smaller values in treatment compared to control. This is exactly what we just talked about in the case study earlier. And of course, as you can imagine, there are many improvements in the subgroups that we can do. For example, gender should not be binary. There are some ongoing challenges that we're facing in this field of study. One of the most interesting ones is anonymity. One of the commonly discussed approaches to help protect vulnerable subpopulation is anonymity. By not providing information such as age and gender, organizations cannot use this information to bias their product and services. However, we have found that anonymity also makes it difficult for responsible software organizations to adjust innovations to better suit those subpopulations. For example, in the case study we just showed, without knowing the gender identity, the impact on female population would not be detectable in the experiment due to the natural imbalance in gender identity in the Windows Insiders population. In fact, all of our inclusive adjustments require knowing subpopulation membership. Consequently, approaches to safely share information about subpopulation membership, to promote trust in the information sharing, and to raise awareness about the potential benefits may be interesting areas for future research. One of the solutions we're adopting to address this issue is to incorporate Atkinson Index to detect fairness issues. Atkinson Index is an econometrics concept to measure inequality. In a nutshell, it measures the percentage of total income that a given society would have to forego in order to have more equal shares of incomes between citizens. LinkedIn published a paper in KDD 2019 using Atkinson Index in their experimentation platform to measure fairness, and we have been working on incorporating the same methodology into the Windows experimentation platform. In summary, we're making many different investments to ensure we can capture unfairness or bias in experiments we run. From the data science technique perspective, we have been looking on incorporating key segments like age and gender and region into the scorecards to help draw awareness for feature teams and provide them with consulting as well as insights from deeper dive analysis. We're also investing in incorporating Atkinson Index and other techniques to address the challenges from anonymity. From the process perspective, we have made process changes in randomized control trials, such that in the experimentation shift rooms, we require feature teams to review the results for key subgroups in addition to the overall level, so that we hold ourselves accountable for shipping products that are fair for our users. As you saw, our platform is adjusting its processes to compensate. Not sure if you noticed, this is the same slide as we showed earlier in this presentation, but in a lighter color, white font. Which one do you prefer? To conclude our presentation, we adjusted pre-launch sample size computations to account for subpopulations of interest. We labeled and segment data for key subpopulations and automatically surface notifications when stat-sig differences occur. And on top of that, we have also been driving culture changes in the organization so that engineers are motivated to use the extra information and adjust their thinking and decisions. And that's all I have for today. Thank you. Do you have any questions?
Thanks, Mary. Let's see. So thanks for the talk. We'll now transition to Q&A. Mary, please see the Q&A tab for questions from attendees.
I see one question. Have you investigated whether gender is actually a confounder in your case study? It might be that dark themes are actually more popular among programmers, where women are underrepresented. How would this change the actions you take to account for subgroups? Yeah, so for this particular A/B test, because it's conducted on a online user research platform, we know exactly who are the people who are part of this experimentation. So it is not a confounding variable in this case, but I think you're absolutely right. Like the reason why we see this imbalance inherited in the data is because we generally run experiments in the Windows Insider population. And in the Windows Insider population, there were more males than females. So it's an inherited data bias, but we still do want to account for it, at least have awareness when such things happen. In your second question, in your Windows setup study, what was the distribution of women and men in the total data set? Yes, so in the case study that I walked through, it was 50-50 between female and male. But in the real setup, like the regular Windows insider population, we have more males than females.